Hello everyone. Today is the 46th day of Leetcode 75 challenge. Let's begin with the 46th question. Question 399. Evaluate division. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. You are given a list of equations, okay, where each equation is represented as a pair of variables. Equation of I is equals to AI BI. Okay, fine. So basically we have been given a equation list which would be like this, okay, a comma b, then a comma b, this take a comma b, I, right, I, j, right, I, j, okay. So you are also given a list of real number values, okay. So this is the equation and this is the value of I, which is represented, which represents the result of division of a of ai divided by bi. Basically, this gives the output of this division, right? A of 1, let it be a of 1 divided by b of b1, right? Then comma, let it be this a2 divided by b2. Okay. So we have one equation array or list and we have one value list. And equation list contains a comma b, okay, multiple times, which is basically different values, and the division of that is contained in this particular value list, okay. Each variable is a string and an equation a comma b with value 2.0 means a divided by b equals to 2, okay. Additionally, you are given a list of queries cjdj where each query asks for the result of division of these particular values. So our task is to evaluate each query using the given equations. If the result cannot be determined based on the equations, we return -1 for that query. And we can assume that equations do not contradict each other and do not involve division by zero. So we don't have to worry about this condition. So that is for our benefit only, that we don't have to consider anything divided by zero or any contradict nature like a by b is there. So which is 1 by 2. So a by b won't be 2 by 3. Okay. The final output should be a list of floating point numbers where each entry corresponds to the result of respective query in the same order. So let me simplify it. So this is what is actually given to us. Fine. So a1 comma b1, when we divide a1 by b1, the output which we get, okay, is this. So basically it means that a1 divided by b1 is 2.0. Okay. Similarly, a2 divided by b2, the value is 6.0. Fine. And we have to find for each query what would be the value of c1 d1 and c2 d2. Fine. This is what the question is asking in the simple terms. We will try to understand this in much more easier manner, or you could say more intuitive manner in the further slides. Okay, but this is the thumb rule of the question what they are asking to us. Fine, this is the equation given to us, this is the values given to us. When we divide a1 by b1, we get 2.2. Similarly, the other values, and we have to find for each query what would be the value of c1 d1, c2 d2, and so on. Fine. And the constraints of the questions are: equations length could be from 1 to 20. Equations of I length would be always 2, basically this one. The length of AI BI could be from 1 to 5, basically the value input, okay. And values length would be equals to the equation length. Of course, they could not be greater because if equation length is 10, value length will also be 10, right? And values could be from 0.0 to 20.0, and queries length would be from 1 to 20. Queries of I length would be always 2 because C1 D1, C2 D2 will always be 2, right? And the length of the CJ Bj would be less than or equal to 5, right? So I hope you understood the problem explanation and the constraints. Now let's move to the next slide. Now let's understand the input-output explanation. So this is what is given to us: the equation, okay, then the values array or the list, and the queries. Fine. So according to the question, what they are saying was, if we divide a by b, this one, we get value as 1.5. If we divide b by c, we get 2.5. Fine. If we divide bc by cd, we get 5.0. Okay. Now the queries are, we have to find what is a by c. The first query is a by c. How to find a by c? Since we have a by b, okay, here, and we have b by c, and if we multiply them, if we use this property of mathematics, and if we cut them, what was the value for a by b? 1.5. What was the value for b by c? 2.5, right? What happens when we multiply 1.5 with 2.5? We get 3.75, right? And through the properties of multiplication, or mathematics, I could say, we got when we take a by b into b by c and multiply their value, we get 3.75. And when we cut this two b's, we get a by c, which is what we need here, right? And that is the same answer written here. Okay. Similarly, for the other, if we take for c by b, right? How to get c by b? Is it possible? We have b by c and a by b, right? Look here, what we are given? We are given c by b. If you could look closely, we have b by c with us, right? And if we do 1 by b by c, which is basically inversely done, or you could say reciprocal of b by c, becomes c by b, right? The c goes up, right? This is the basic property of a mathematics, right? Similarly, if this is done, so what is the value of b by c? It's 1.25, right? And if we do the reciprocal of it, or if we just divide it by 10, okay, what happens? 10 goes up, 25 remains in down, right? And when we divide 10 by 25 up to the decimal place, what we get? We get 0.4, correct? So this is what we got here. Now let's take the BC CD, okay? BC by CD, okay? We have been already given BC by CD, which is 5.0, right? So it is written here. Now what is the next question? We could say next query. If you could see, this is the reciprocal of the one which is given to us, right? If you pay attention, it is CD by BC, right? And we already have BC by CD. And if we again use the mathematical property of the of doing it reciprocal, what we get? We get CD by BC. The value which was given to us for BC by CD was 5.0, right? And if we do 1 by 5.0, what we get? So after doing 1 by 1.5.0, what happens if we do the calculation? So basic mathematics, multiply both numerator and denominator by 10. Okay, so it cuts it by 2, and 2 cuts it by 5. So the output comes out to be 0.2, right? This is what we got here. So this is the results for each division. So we have to basically find this. Okay, so let's look at the second example. So we have been given equation for which is basically a by b, and the value for that is given to us is 0.5, correct? And the first query is a comma b, which is basically a by b, so 0.5 will be the output. Second is b by a, which is basically reciprocal of a by b, so it becomes b by a. We have already done this here. So 0.5 will become, if we multiply 10 in top and we get 5, right? And if we divide it, we get 2, right? In decimal. So this is what we have here. Then we have a by c, right? Now, if you could see, we don't have c here, right, in the given equation. So we cannot consider that. That's why the output comes out to be -1. Okay. Similarly, x and y, it is not mentioned anywhere in the equation, right? So we cannot use that. Therefore, the output for that also comes out to be -1. Here in the question, it is already mentioned that if the result cannot be determined based on the equations, return -1. Okay. Point number 5. Similarly, here we don't have x or y or c. That's why the equation cannot be determined. Therefore, the output comes out to be -1. Basically, that particular thing is not present in the equation. Okay. So I hope you understood the input output explanation. Now let's move to the next slide. Before going to the further slides, let's understand what is depth first search in graph. Okay. So DFS, which is depth first search, is a graph traversal algorithm that explores as far as possible along each branch before backtracking. So in a simple language, if you remember in tree also there was DFS. What is the simplest and the common difference between a tree and graph is that suppose this is a binary tree, and if you connect it, it is a graph. So a tree has to be unconnected, whereas graph could be connected and unconnected both. Okay. So let me draw a graph. Okay, let this be a graph. I'm trying to draw a directed graph here. Okay, okay, and this one, then will come here. Okay, so I have just this is a random graph which I have drawn. Okay. Suppose you started with 1. Okay. From 1, where you can go? You can go to 2 also, and you can go to 3 also. Correct. So, but you cannot go twice all simultaneously, right? Into both of the nodes. So what you will do? You will think of going to the 2 first. So you went to 2 first. Okay. Then you tried going after from 2. Then you tried going more down, more in more depth, but you were not able to because the arrow was pointing in different direction since it is a directed graph. So what you did, from 1 to 2 you went, then you came back, then you went to 3. Okay, I will write it this way. You came to 3, then you could see that from 3 you can go to 5 also, right? So you came to 5. From 5 you cannot go to 4 because the direction is this way. But from 5 you could go to 6. So you came here. After that, you saw that you cannot go anywhere else because it is the end. So you came back. That is a backtracking part. Okay. And if you could see, explore as far as possible along each branch. Okay. Basically going to the depth. So we went to the depth. Then you came back, backtracking. After that, you could see that you cannot access 4 or 5. Right. So what you do, usually if you remember, we draw a for loop to go to each and every node. 1 was visited, then 2 was also visited, 3 was also visited, 5 was also visited, 6 was also visited. It was the 4 which was not visited. So when we go through a for loop, which basically goes from 0 to n nodes, and we mark everyone visited, right? So when you come to 4, you say it is not visited, so you keep it as 4 here. Okay. But you cannot go to 5 because it is already visited, and 2 because it is already visited. So this is what a depth first search looks like. Okay. And how it works in a theoretical manner, if you could see, we start with the source node. It could be anything. It could be 2 also, it could be 3 also, right? But I started with 1. We mark it as visited, visit one unvisited neighbor recursively or using a stack. So this is not necessary. Recursively, when we use, it already uses a stack space. Okay, that's the thing. And we mark it as visited so that we don't visit one node again and again. We backtrack when no unvisited neighbors remain. If you can see, there are two cases when you backtrack. One is that you reach the end, or one, for example, if it was a circular, suppose it was a circular graph. Okay, suppose I am marking with this yellow mark. Okay, the latest mark. Suppose instead of going after 5, we are going to 4, and we are going to 2, and not this one. Let's take it as this. Okay, so the path now is this way. Okay, it's a circular one. So when you start with 1, when you go to 3, when you go to 5, then you go to 4, then you go to 2, then when you come to 1, you see that 1 is already visited, right? So you go back. So this is another case when you backtrack. Okay, the two cases I told you. And DFS can be implemented using recursion. Okay, and this is not necessary explicitly stack. It was it's an uncommon practice, but I just have written here that if you want to use, you can do it. And why is it efficient? The time complexity comes out to be V plus E. V means vertices, E means edges. What are the edges? These are the edges. What are vertices? These are the vertices which are also called as nodes. And each node and edge is visited once. Okay. Therefore, the time complexity for comes out to be V plus E. V means for each vertex, you might go to n number of edges, right? And space complexity is OV of O vertices because we store number of vertices in the array. Okay, we don't store the edges also. That is not possible. And for recursion stack or visited array. Okay, and it is efficient for graph traversals where full exploration is needed. As you can see, we needed a full exploration in this case, and solving problems that require backtracking or component discoveries. The component discoveries, I will get a question ahead, then we'll look at it. Now, where we can use this DFS? Okay, I've written some of the question examples and topics where you can use. Suppose if you get a question which is related to connected component detections, okay, like in undirected graph, DFS can be find and label all disconnected components. Disconnect components are basically, suppose this is a graph, this is another graph, this is another graph. So there are three disconnected components, but they are a single graph, but all are disconnected. Okay. So output for this particular will be 3. So in this case, we will use DFS, not DFS. It is not much helpful in that case. Or in the cycle detection, also you could use that. Suppose if the graph has a cycle or not. Okay, this is a cycle, correct? And you could find the questions in for directed graph, for undirected graph, right? And topological sort is the DAG. So when you have to check for a DAG, DAG means what? Directed acyclic graph. This stands for DAG. Fine. Directed means you have an arrow only in one direction, not both directions. Acyclic, it does not contain a cyclic. Suppose this. This does not contain a cycle, right? So this is what a DAG is. So if you have to look for a DAG, whether a graph is a DAG or a question related to the DAG, then in that case you have to study about topological sort and use that concept there. Okay. Path finding without weights, when you have to find a path in a given graph, okay, like solving maze-like problems, okay, without weights, and there could be also a path finding with weights, fine. Solving puzzles like Sudoku and coins and all that stuff. Breach and articulation point detection. In networks, DFS helps identify critical connections, so removal disconnects the graph. So basically, if you have to look for articulation points and you have to remove that, or the bridge you have to remove that, in that case, we use this concept, or we use the DFS in that case. We will follow up with this all these questions as per our sheet. And strongly connected components. Like for example, if you could look at Kosarazu's and Tarjan's algorithms, both uses DFS to find SCCS is in directed graph. Strongly connected components are the components which cannot be break into multiple pieces, right? Okay. So I hope you understood the depth first search in detail. I have not gone in much more depth because it is not necessary. Because if you are studying graph, you should already know about this topic. But yeah, I have figured out some of the things of DFS which will help you in solving the problems. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's do it by understanding the goal first. We are given a list of equations such as a comma b, which is 2.0, and this will be string always. Okay, which mathematically means that a by b equals to 2.0. This is what we understood. Now, along with this, we are also given a queries a comma c. Okay, like this. It is like this. Okay, which is also a string where we need to determine the result of a by c. Right? We saw how we can determine this particular thing, so this is clear to us. So if it is possible to derive the result using the equations itself, indirectly a by b, b by c gives us a by c, which we already saw, right? If a by b is given and b by c is given, so we could get a by c, right? By multiplying this particular thing. This b gets cancelled and we get a by c. Otherwise, if we don't have such values, then we return -1. That's it. Now, our task is to build a way to connect and reason about these variable relationships and compute the result of each query. So we already know that we are following the graph playlist right now, or the graph topic right now for the 75 blind challenge. But we know this is a question of a graph. But how a graph fits in this particular question? This is what we have to think about, right? What is the thing that if you see the question is purely mathematical based, right? But how it is a question which is related to a graph question, right? So we have to build up that intuition before going to the approach or the solution directly. Fine. Let's do that. Now let's visualize the process. Fine. Suppose you are given the equation a by b, which is 2.0, and then we're told b by c is 3 point, right? So we start to notice a pattern. Okay, what we start that if this is given, that means if we multiply a by b into b by c, basic mathematics, so we get 6.2, right? So yeah, okay, we cleared this out by using our mathematics, by using our brain, fine. But that seems straightforward, but soon as question starts popping up that, okay, so if a by b is there, then it could be b by a. Okay, if it is b by a, then what happens? It is not 2.2 anymore from a by b. It becomes 1 by 2.2, right? Then we do the reciprocal and get the result for it. Correct? What is the query c by a? Suppose, let's cover this particular case also. Suppose we are given a by b, c, oh sorry, a by b and b by c, and we are asked to find c by a. Okay. Previously, we were able to find a by c, right? By we were deducting B and C, B and B from both the equation A by C, right? Now what happens to the C by A? Now what happens to the C by A is that if please pay attention, if A by B is there, what if we do 1 by A by B, reciprocal of it, just simple as that, it becomes B by A, value also becomes 1.2. Okay. Similarly for B by C, what happens? We do the reciprocal, we get C by B, and value also gets like this, right? Now, what if we multiply B by A into C by B, and values are 1.2 into 1 point, sorry, 6.0, right? 1 by 6.0. So what you can see, we could deduct BB, we get C by A, okay, and this gets multiplied and we get 1 by 6.0, right, for C by A. Okay, so we covered two test cases here from our side that, okay, if A by B is given and we have to find B by A, we could just do the reciprocal of it, okay. If A by B is given, B by C is given, and we have to find C by A, because A by C we figured it out, right? What about C by A? If C by A is there, that means we have to do the reciprocal of this particular given equation if we have that, okay. Now the third case, but what if we get a query like E by A and E hasn't appeared in any equation? See, look, we don't have E in any of our equation, right? So is it possible to calculate something which we don't have, right? We could calculate something from which we already have, right? We have A by B, we could calculate C by A from it, right? Or A by C from it. But we cannot calculate E by A, right? Because we don't have E in there. In that case, we just return -1. So this is the three important cases which you can figure out from our simple mathematics calculations, right? Now, since this is a question for graph, we already know that, right? But don't worry, in an interview, you will be given a hint. If you have already solved this question, it will be simple, easier for you to do it, right? Or if any variation is also given to you. But if you are new to this question in the interview, don't worry about it. If you do the mathematical calculation of this way, the interviewer will surely give you a hint of doing some kind of graph situation stuff, right? So please keep that in mind. Don't worry about it. This is the one of the if this question comes in one of 10 or 20, where the hint has to be given to you, otherwise you won't be able to go or move forward for the particular question. Fine. So this is the three things we figure out. Now, what we tried connecting these variables using the known equations for every equations like a by b equals to 2.0. So suppose a by b, we try to connect a by b like this, okay, with a value of 2.0. Oh yes. Now b by c with the value of 3.0. Makes sense? If we have to look for c by a, wait, let's do with a by c first. Then what was the value of a by c? If you remember, it was 6, right? 2 multiplied by 3. If in this path, if you could see, if you start from here and you go here into B and you come here and you multiply the edge values or weight of the edges, what you get? You get 6, right? Get 6. So are you getting some kind of idea here? Are you getting some kind of hint here what we have to do actually? Right? If still now you're blank with a particular thing, no worries. Let's understand this particular thing in much more depth. Okay. So please remember this particular cases. It will be helpful for us to figure out the stuff, right? So let's try visualizing the process again. Okay, let's continue. Now all the variables starts forming a network, right? Let me did already. Let me create the graph again. A to B, B to C, 2.0, and this is 3.0. Weight of the edge. Okay. So without realizing it at first, we have started treating it like a weighted graph. Okay, we have taken it as a weighted graph. Variables are the nodes. Each equation forms two directed edges. Why two directed edges? Let me tell you. If you remember, in our case, we saw that if A by B is given, fine. But if we have to look for B by A, then the value would be 1.2.0, 1 by 2.0, which will be 0.5. Now for that, what we have to do? We have to reciprocate it, right? So A by B is this, and this becomes B by A, right? Yeah. So we connected this in the reverse manner, right? And the value comes out to be 0.5, right? So that's why the connection of the graph has to be in the bidirectional format, because A by B is given to us. What if we have to look for B by A? B by A is the reciprocal of A by B, right? Similarly, for B by C, to find C by B, we have to go back, right? And so some value becomes something like 0.333. Okay. So this way, you could get A by B also, which is 2.0, B by C, which is already given to us basically. A by C, how you will get A by C when you multiply this particular two values, right? Two equations, which basically means going from A to B and B to C, traversing the graph. You are traversing here. Please keep in mind you are traversing here. This is another point of finding out that why we are using a graph here. Okay, this makes sense. So if you come to C, it becomes A to B, B to C. Basically, total equation from A to C becomes 6, right? If it is C by A, then what? You go from C to B, then B to A, and if you multiply these values, you get the value of C by A. Am I right? Yeah. So this is the thing. Okay. So from here, you could figure out that okay, the traversing in the particular equation makes sense of using a graph concept in this particular question. Okay. Now, and once the network is formed, the answering the queries A by C becomes a matter of time, like I have already explained you. This entire realization builds up to one clear strategy that we need to explore paths between variables and multiply ratios along the way. If we don't have any character in the path which is mentioned in the query, we return -1 in that case. Suppose if this is also, let's say this case also, E by A was given to you. Do you have E by A anywhere? No. But you have A, right? So what you do is basically searching in a graph, okay? Just take it as searching in a graph, okay? So you find A here. Then from A, you went to B, no issues. So you multiplied 2, you got 2.0, okay? In a variable, suppose less, well, okay? Then from B, you went to C. So you now the multiplication is 6.0, right? Now from C, no way to go, right? This means that you completed the traversal. Therefore, if you didn't find E anywhere, you will return was -1 at the end. Makes sense? Because there will be only one component of the graph, right? Because they have to be connected to each other. Otherwise, it will make no sense of forming this particular equation, right? Suppose if there is A by E and which is 2 point something, okay, and there are much other equations A by C or something like B by B, and you have the values for that also, don't worry, but you have E only one time, right? So E will be connected from this way, right? But still you got E, right? So if you traverse complete graph and you were looking for F, if you didn't find here, what you will return? You will return -1. Okay, there will be one component. There cannot be two components of the graph. Please keep that in mind. Okay. I hope you understood this visualization process. Now, how we can simulate this? Okay, this is the important thing. Let's treat each variable as a node, which we did already. Okay, and each equation like A by B as a bidirectional edge. A to B 2.0, B to A 1 by 2. Okay, this will be basically done as uh, adjacency graph we will create of A dot append B comma the value which was given to us, right? Great. Then this will be B dot append simple with C 1 by where, not C A. Okay, this makes sense, right? This is a reciprocal value. This way we will build up the graph. To build up adjacency list to represent the relationship between the variables. Okay. Add B to the list of a with division value. Add a list to a B with a reciprocal value, which we did. Now, for each query, after this, we have to look for the queries guide, whatever is given to us. So what we'll do in the query value, query list, we will take out. Suppose this is given to us, right? A by B. Suppose A by B is given and B by C is given, right? What we'll do, we will take this out. What we'll do, we will make it as like U, okay, U as A, B as B, which means that U is going to be, which is a general understanding of the graph, right? We will search for this value or this value. If we find any one of the value, we will do the iteration in the DFS, okay, or in the easy manner, we will start a DFS. Because if you don't have either of the value A or B in the first search itself, there's no use of traversing, right? It will make no sense. So we will return -1 in that case directly. But if you find any one of the value, we will immediately start searching from that point from that particular node. Okay, then we will multiply each and every edge I have written here, and for each query, we perform DFS starting from A trying to reach C while multiplying the weights which comes on the way. Okay, and even if the paths are going this way, suppose, and you came from here to here, you will roll back, right? If you come back, then the multiplication gets divided automatically. The recursion takes care of it itself, so don't worry about that. And then it goes to this particular path, fine? So if you after traversing the complete DFS, if we don't get any the other value, then we return -1. So in the two cases, we will be returning -1. Okay. One, the first iteration when we take the query before starting the DFS, then in the DFS when we return the value. If we reach the destination C, we return the multiplied result, which represents the evaluated division. Simple. If we cannot reach C from A, we return -1. Simple as that. To avoid cycles, we repeated visits. We use a visited set, which is a common practice in using a DFS traversal. Okay. So what we figure out from the problem? Each equation defines a relationships that can be changed with other to derive a new result. Chain means A can be derived to B is derived to C. Then from A to B to C, we can get A and C as a path. To answer query, we need to find a path from one variable to another variable and multiply the value along of A. It is basically what we saw multiplying this particular thing and getting A by C and converting into a graph. What we saw that A goes to B goes to C, and we have to multiply while we traverse, right? That is the thing which we understood. This naturally led us to DFS because using DFS also makes sense. Yeah, but it is less intuitive from my end. But using DFS makes it much more intuitive to the particular problem. If a variable doesn't exist or no path between them exists, we just return -1 in that case. In the end, the model of the problem is a weighted connection system, weighted graph basically, weighted bidirectional graph. Okay, solving and navigating and multiplying through the known ratios. So this is a very interesting problem. I hope you understood the problem intuition. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. We are given an equation a by b 2.0. Okay, we know this. Okay, mathematical relationship. So what we do, we construct an adjacency list. We like name it as adjacency ADJ for equation u comma v basically from we traverse the equation. Okay, what will happen basically is that what will run a for loop u comma v in the given equation list. Okay, everyone knows that u comma will give us the value for each uh, value. Okay, so the equation list is this way, right? So u comma will give me the value from this thing. Okay, or you could say the nested block. Then what we could do, or what we will do, you create adjacency and u to v, which is originally given to us, append the v with the value. Okay, then adjacency of v, we append u with 1 by val. Okay, this is what we will do. Okay, this will create the adjacency list completely for us. Then we will declare a result array or list to store the answer for each query. Okay, to store the answer for each query. By this allows us to move in both directions during the traversal. In division, it's reciprocal, enabling us to change the variable relationship. Okay. Now handle queries and initialize DFS traversal. Step 2. Now for each query, what we will do, we will again make a for loop which will have source and destination. Okay, given in the queries list. Let me clear this up. So yeah, so we will take source and destination from the queries which will be given to us. And what we will check, if we have the source in our adjacency, not in. Okay, not in. I will just give this exclamation mark, or destination in, not in our adjacency. Okay, if we don't have source, either source or destination in our adjacency list, we will do what? We will result which we created already here. We will append -1 to it. Okay. Otherwise, we will create a visited set because we will have to keep unique value to it. Okay, all the time. Therefore, we take set and put the values there. Okay, because set store unique values. And for each DFS call, we will have this particular thing. Okay, we will declare this and we will pass it here this way. DFS adjacency list, source, uh, destination, of course, which we got from here. We visited list. Okay. Now, why we have taken this res variable? Because the DFS call will return some product. If you remember, we have to find the value of a by c or d by e, whatever, right? So for that, we need something, right, to store the variable or the value return. That's why we have declared this variable here, and we have initialized the DFS function for it. Now, also keep in mind that we have used a set here in the visited list for the visited list. Okay, we could also use a list, but we have used set so that the values in it tends to be a unique one. Also, the adjacency list will be created as some kind of a different way this time. This will be of form adjacency equals to default, which will be of list. Basically, what is a dictionary? Dictionary is key value pairs, correct? But in this case, key will be there, which is great, but the value part will be a list, right? So if A is there, there could be B, C, B, right? For B, there could be C, D, A, right? So that when this will help us in searching the values. If you remember, we were searching the values here, right? We were starting the DFS, we check if both source or destination, source and destination exist in our graph. Source and not and basically or either of the one has to be there, right? For that, what we do, we pass the source and destination in the identity list, and we check that do we have source or the destination in the keys, right? We look for the keys when we do the searching in the dictionary, right? If we have, what we do, we pass the adjacency list, okay, and all the stuff, right? Let's understand this in much more clearer in the other steps and in the code part. Now in step 3, we perform the DFS to explore an accumulation of the result, right? The DFS function explores neighbors of the current variable. So since we had A, B, C, suppose some variables were there like this, okay, this is the key, these are the values, let it be C, and let it be, I'm just adding some random values here, right? E, F, C, let it be G, E, L, okay? So random values are written. So what this means that A is connected to B, and it's like A is connected to B, A is connected to C, A is connected to P, okay, and it has some values in it, right? Since it is a weighted one, it goes like this, okay. Now, how the weight is stored? Let me write that also. It is stored like A is there, B is there with value 2, okay, this way. C is there with value 8, this way, okay. So this is the value are stored. Let it be 2, 3, something like this. And since B is also connected to E, F, and C, so this is how the graph will look like, or the adjacency list will look like. Fine. If you have created only using list, the searching part might have been more difficult to do, right? But in using the default dictionary, makes it easier for us. Now, at each step, if the current variable matches the destination, like when we are doing the traversal, DFS traversal, if the source matches the destination, we return the product. Why source? Because in the parameter of the DFS function, I'm just writing the half of it. Okay, source and destination is given to us, right? And some other. So what happens when we call the DFS again? We never change the destination. Okay, we always change the source. Suppose we started with 2, so it came to 3 now. So and destination is 5 somewhere here. Okay, so the source will be changed from 2 to 3. Okay, and the value will be multiplied for this particular edge. Then again, it will go from this case, some values will be there, it will get multiplied, the 7 to 5. So when source becomes 5 and destination also becomes 5, we check if both are equal, we return the current product, and we basically backtrack the DFS from there. Okay, or we return the DFS from there. Otherwise, we mark it as visited, simple, and if we explore the other nodes. Okay, so recursively call the DFS on the neighbor. Neighbor is basically the current node. Multiplying the product. Product is basically the value till you stored till now. Okay, and the value of the edge. That's all. If the valid result is returned, then we propagate it backwards. Right? Basically, if it is not equals to minus 1.0, we return the result. Okay. Suppose you are doing the DFS call. Okay, and you got the product, you got the base case, right, and you return the call. Okay, I will explain this code in the code side. Fine. So if the result is not equals to -1, we just return the result. Otherwise, we go to the outside of the function and return -1. This simulates the chaining equation, and the accumulated product reflects the computed value along a valid path. Okay. Already step 4, after doing all the queries, we come out of the loop. Okay, and we just return the list where we stored every value for it. Okay, for every each query you could say. Because for each query we do a DFS run. Please keep that in mind. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. So this is the given function to us, and we have written the code here. This is the default dictionary which will be created, and it will be created in the form as I already explained it to you. This will be b comma 1 c comma 2, so that when this is created, right, and when we do the for loop in the queries for source and destination, sorry, we check if source is in the adjacency dictionary or not. It becomes it's a adjacency list, but it's a dictionary, right, with a form of list. Okay, so that makes it easier to look for the values. I hope now you understood what we are trying to do here. And if the values are not present, we append -1 to the particular query. Otherwise, we take a visited set for the unique values always. We call the DFS function here for this particular query. Okay. And what happens in the DFS call here, if the source is visited already, we return -1. Suppose what happens if the graph is a circular one. Suppose, okay, this is the source you started with. Suppose you came here, you came here, you came here, you came here, then you came back to source again, right? That means a circular graph and you didn't got the value what you were looking for if it is already visited. Therefore, we return -1, right? Or if you end up coming to the same source or you visit the same source again, that means that you didn't find the destination and you have to return -1 in that case. Okay, it's a simple understanding of the circular graph it could be. And if you find the destination, the source equals to destination as I explained earlier, we return the product. Okay. Otherwise, we mark that particular source as visited. Okay. Then for the neighbor and the value for the adjacency of the source. I hope you understood this particular thing. We call the DFS again with the updated neighbor. Destination remains the same and product. Product is basically product. If you see, we have passed 1.1 initially because we have to multiply value with 1, right, to get an answer. So if this is the graph. Okay. You multiplied, we had 1, right? You came from here to here, and the edge value was 2. So you multiplied 2 here. Okay. Product with value. It became 2. Now this 2 will come here. The new adjacency neighbor will come here. Okay. Which is basically this one. And again, when you come to this particular loop, you do the multiplication again, right? The product was what? 2. And the value for this particular is stated with 3. Okay. So it becomes 6. So this is what happens here. And if the result is not equals to -1, what happens when you complete the whole traversal and if the result is not equals to -1, we return the result. Okay. Also, how this happens is that suppose you reach the destination. Okay, you got the destination, so you return the product. What happens now? We go back, correct, with the product. Okay, with the product to go back. So this call is done, right? You have the value here, the product value, you have it here, right? So if the result is not -1, we return the result itself. I hope you understood this. Let me draw it and make it understandable to you. So you got the destination here, fine. So for example, you got the value here. You got the value here and the product comes out to be 8, suppose, right? And you started from here. So what happens? You send back the product here from this particular code. Okay, 8, then again 8, which means that this particular DFS call is done, right? If you please have the understanding of the recursion before going to solve any graph questions, because that will help you to understand the problem in much easier way. Okay, so you get the result of 8 in here, right? Then you check if the result is not equals to -1, then return the result. Okay, otherwise, if the result is equals to -1, then you return -1 at the end after the complete iteration. Okay, now the time complexity for this particular question comes out to be n plus q is query, then n is the length of the values and the equation given to us, and q is the length of the query. All right. So what happens for each n equations, right? There are multiple equations, right? We add two directed edges, forward and reciprocal, if you remember, which takes O of n time, correct? Because this is the given equation given to you. For each equation, you do both sorry, 1 by v and v, okay? So it takes O of n time complexity because we create a bidirectional graph using that. Then we do the DFS traversal for per query. The length of the per query will be q, right? And for visiting all the nodes and edges once, right? For each query, we call the DFS, which takes O of n time complexity in worst case. Therefore, it becomes, for each query, one DFS is called, it becomes Q into n. I hope you understood this. Therefore, the complete time complexity comes out to be n plus Q into n. And the space complexity, n is basically for storing the edges, okay? And Q is basically for the result list. The list will be of size the query, right? That's right. Or you could write it as n also because the length of the queries and the values and the equation would be same, but I have written separately to explain it in a better way. And also the n and also some space will be covered by this visited set also, which could be equals to n or less than n. Fine. So I hope you understood the space and time complexity for this particular code and the code explanation. So let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So I have already brought down the code here for your better understanding. So first, let me draw the graph for you. Okay, so I have drawn the graph here already for you. Now let's do the diagram. Okay, so this is the DFS function, and this is the function which is given to us, right? So we created this graph using this adjacency default dictionary, which will look like some this like this A. Let's let it be here. A appended to B. Okay. So what happens? It becomes like this. B with value 2.0. Okay. Then B comes here with A with 0.5 as the value. Right. Similarly, for B to C, there would be another path which will be this way. C will be here and 3 value will be here. Okay, this way the graph will be created. I hope you got the intuition. Now we have the result list. Let me draw it somewhere. This is the result list. Okay. Now we will start for iterating. Okay, for source and destination in queries. Let me draw it already. C will have B with value C to B is 0.66. So I have values from A to B, B to A, and B to C, and C to B. Okay. So it starts with the value. First equation which has A comma C. Then we check whether we have A or C in our dictionary. So in this particular case, so we have it, right? We have A also and we have C also. So we don't have to worry about it. So we create a set of visited and we call the DFS function. We pass these values here, source and destination, which is basically A and C, visited, and one is the product. Now we come here. What we have? We have A, C, visited, and product as 1.0. Okay. So if source in visited, it is not. So don't have to worry about it. We don't have to worry about this particular case also. Now we mark this source as visited, A as visited. Then we go for the neighbors of the A. Okay, the neighbors in the value. So what we get for the neighbor of the A2 we got B, right? So B is passed in the neighbor. So B is passed as source now. Okay, from here. Now product is what? Product we had already one, right? And the value for this particular edge was from A to B was 2, right? So 1 into 2 gives me 2.0, right? So our product in the main function gets changed in the recursion call. It becomes 2.0. I will write 2. Please keep in mind that it is already a float written. So what's the thing? Okay. So we have 2. Now, is the source visited? No, B is not visited. Neither it is equals to the destination. So we add it into our visited path or the set. Great. Then we go for the neighbors of the B. So the neighbors of the B is right now C itself. So the neighbor becomes C now, which basically becomes the source here. Correct? Then the product changes to, since we already had 2, right? So 2 gets multiplied by 6 or with 6 or 3. Sorry, my bad. 3. So the product which is sent in the top becomes 6. Then is source visited? Of course not. Is source equals to destination? Yes, both are C, right? So we return the product. What is the product? 6 here. So what happens? We're standing in this node, correct? And the product with you have is 6, right? What happens when you return the product? What happens? The DFS call comes back here. Since it cannot go in this particular direction, it goes back here. right? Now, since the call is done, so the result has the value, what? It has the value 6 with it, right? So this particular function returns 6, this result variable, and since the result is not equals to -1, we return this result. So this DFS call returns here 6. So we append this particular thing into our resultant list. Okay. If you could see, the resultant for A, comma C was 6 itself. I have not taken the decimal points, but that is what it is. Okay. Now let's take another example. Since it will be a lengthy if you do a try run for each equations, let me take another example such as let's take x comma x. Okay. Now x comma x. What happens? We come here. This part is already done, right? So we go for this query number last. In this case, please keep in mind we are going for the last query. Okay. The last query we check. Okay, x comma x. Source not in existence list. We don't have x. Neither we have another x. Okay, we don't have both either basically, right? So what happens? We result append -1 into our resultant here itself. So this is done. Then let's take another query. I'm not going serially. I hope you understood that particular thing. Okay, I'm taking some unique cases here. Let's take b by a. Okay, this is a unique case. For the b by a, what happens for the query? We check is source is in the adjacency dictionary or the destination. Either any of the one is there. Yes, we have both actually. So no worries. We create another set. Okay, we pass the values. Right now we have source as b and destination as a, right? Okay. Is the source visited? Of course not. They are not equal also. So we mark it as visited now here. Okay. Now we go for the neighbors of the B. Now, look, the neighbors of the B are C and A both, right? So since we are concerned with A, so I'm skipping the part where the B goes to C. Okay, does the calculations, then comes back. Fine. But now I will directly go to the A, like adjacency. Okay, suppose it went to A directly. So product we already had 1.0 passed. Okay, so the neighbor becomes A. Destination is of course A already. The value becomes into multiplied by 0.5. Fine. So the product which we have 0.5, the source changes to A. Okay. So it is not visited. Of course, source is equal to the destination here. So we return the product immediately. The product is 0.5. So from here, the product is written to B because we started from B, right? And the recursion call is done. So result here stores the value 0.5 with it, and it is not equal to the -1. So we return the result which is 0.5. So here we get 0.5 as the resultant. Okay, and we append it to our list. So for this query, if you could see, we have 0.5 as the output, right? So you could do for the others, A, comma E and A, comma A. It's simple as that. A, comma A, there would be no iterations, and A, comma E, it does not exist. So it will find the value here, since we will get the A here, right? So we will call this function, but we won't find E anywhere. Okay, we won't find destination anywhere. So this will return -1. So please do the iteration or try run for that particular case. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code, and also the DFS concept if you don't know about it. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Let's create the adjacency dictionary or list, I would say, default bit of list. After that, for u comma v, also the val in zip of equation comma values. So this particular zip will help us to zip the values from equations which will be taken by u comma v, and values will be taken from the variable val. Right. So adjacency of u dot append v comma val adjacency of V by Fn U, comma 1 by Z. Right? Let's declare the resultant result vector for each query. For source, comma destination in queries. If source not in adjacency or destination not in adjacency, what we do? Result dot append minus 1.2. Okay, else we create a visited set. Result, then we call the DFS function here. Adjacency, source, destination, visited, and the product. Okay, and we append the result which we get into the list. We return the result list. Let's call the DFS first. Now DFS self, comma, adjacency, source, destination, visited. It will be VIS itself. Okay, will be product. So, fine. If source in visited return -1, circular graph or we have already checked in. That's why we don't have to do it again. That means the value is not there. Source equals to destination. We return the product. Okay. After that, put that in the visited set. Okay. Now for instead of neighbor, I will write. Let's go for the neighbor itself. Neighbor, neighbor, and the value or the edge value basically the weight of the edge. And you can see on the source node result stores the self dot DFS and we pass the neighbor here. Now we pass the recency list, and we pass the neighbor, then we pass the destination which will be same every time, visited, and the product multiplied by the value, right? Now after that, if result is not equals to minus 1.0, which means we have found some value and we will return the result. Else we return -1 means we didn't find the destination. Okay, now let's try submitting the sample test cases. Finally submit the solution. We successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.